So, hello everybody. My name is Sunil. So, I am from Department of Applied Mechanics, Indian Institute of Technology, Delhi. So, my topics is on mechanics of fracture in silicon using near-tip analysis. So, the motivation of this topic came from the crack propagation in polycrystalline solar cells. So, the polycrystalline solar cells, there are PV solar cells. There are two types. One is monocrystalline and polycrystalline. Here you can see the polycrystalline solar cells. There are wafers and these are the crystals. So mostly the polycrystalline solar cells are used instead of monocrystalline because of this cost sensitive and being very high cost. The thickness of these wafers are reduced. These wafers are reduced and made it very thin. And being a very brittle material, the silicons, the microcracks formed, and due to different loading conditions, the crack propagates and reduce the life efficiency and the service life. So what are the different loading conditions? The different loading conditions are during the snow and wind and dust, the temperature, humidity variation, transportation and installation. So here in the
you have to be careful. Yes, you have to be careful with your finger. If your finger is too close, you.
So here this is a experiment of a silicon wafers, polycrystalline silicon wafers. So we have done a tensile test and we can see that the crack propagation here, the cracks propagation are either transgranular or intergranular. So this is in simulation models of polycrystallines. Here at some stage before crack initiations, this is the crack, and after crack propagations, you can see the different type of crack propagation: transgranular, intergranular, from transgranular to intergranular, and grain boundary cracking. So in this discussion, we will do only the transgranular crack propagations. The focus will be only on the transgranular crack propagations. So to understand the mechanics of the crack propagation in polycrystalline silicons, we have taken the bicrystalline silicon first, and once we understand the mechanics of this bicrystalline silicon, we can go into the polycrystalline one. This is a bicrystalline this is a schematic of bicrystalline silicon. This is crystal 1, crystal 2 separated by grain boundary. They are of different orientations, and the simulations are performed under these conditions. Can you show the simulations? Here you can look here. This is the stress and plot, and the crack is propagating here. This is crystal 1, this is crystal 2. There is grain boundary. So there are different stages of crack propagations. So now the crack will interact in the grain boundary. Now the crack will propagate into the crystal 2. Here you can see the wavy surface, and we will discuss this wavy surface in the next part. Let me close. So there are three different stages of crack propagation here: crack propagation in the crystal 1, and then crack grain boundary interaction, and crack propagation in crystal 2. In these slides, we will discuss only the crack propagation in crystal 2. Here you can see the crack is at the grain boundary, and when it enters into the crystal 2, a void will create here, and due to void coalescence method, the new sharp crack will form. So here the crack is here, and the crack will try to propagate in the negative directions, and here again this crack will grow in this positive directions. So in this way, a zigzag crack path will form, and the crack will propagate in the crystal 2. So to do the understanding the mechanics of this crack propagation, we have to determine the instantaneous crack tip velocity. You can see that the crack is moving, and crack has some velocity. So this velocity has some impact on the crack propagations. So this is the crack tip extension versus time plot, and from this plot we have got the crack tip instantaneous crack tip velocity of different positions. So using this instantaneous crack tip velocity, we can use it in the understanding of this mechanics. So how we will determine the stress intensity factor ahead of the crack tip? So you can see there are atoms ahead of the crack tip. This is the atoms above the crack plane, atom below the crack plane. Using these atoms, we can plot a sigma versus R plot, and from this sigma versus R plot, we can determine the stress intensity factor. And because the crack is moving, to make a understanding of the mechanics, we can do the equivalent static SIF. So to determine the equivalent static SIF, we have to divide this with a factor of this kappa 1V. So this kappa 1V can be determined from these expressions. So there you have seen that the crack is moving in a zigzag fashion. So there is mixed mode loading. So to determine the stress intensity factor, we have to use this mixed mode loading. So we'll discuss only one stage here, and all other stages can be explained in that way. The crack is here. So along this plus 45 direction, the K effective is at 1.20, and at minus 45 degree directions, the K effective is 0.83. So from the next stage, the crack will propagate along the plus 45 degree directions. Here you can see this in the next stage, the crack will propagate in the plus 45 degrees directions. So in that way, if you take all the other all the other stages, we can understand the mechanics of this crack propagation, that the crack is propagating in the most of the cases when the stress intensity factor is higher than the critical stress intensity factor. And at some stages, just like the void coalescence stage, the crack there is a void is created and crack is propagating, and at this stage the K effective is less than that. So the details of this can be found in our publications. So we have shown the near tip stress field and what is the limitation of this stress field. For example, when the crack is close to the grain boundary, at this stage there are different atoms here which will affect the determination of the stress intensity factor at the grain boundary. And there is a sharp variation of the stress field from when you move from crystal 1 to crystal 2. So the fitting methods that we use to determine the stress intensity factor cannot be used. So to overcome these limitations, we will use another methods. So in this here we will use the energy release rate methods determined at the that will be used after determining the CTOD, crack tip opening displacement. There are two different methods of determination of CTOD: the direct method and the 90-degree blunt method. Using this direct method and 90-degree blunt methods, we have calculated the CTOD, and from the CTOD, the energy release rate has been calculated. So whether these two methods, which one is more appropriate for our calculations, to understand that, we have calculated the J integral using the volume integral method instead of the conventional line integral methods, and we have compared with the J integral of the continuum methods. So when you compare these four results, and from there we can determine the appropriate energy release rate, appropriate methods for determination of energy release rate. So we have performed a simulation of single crystal silicon. So from this, the using the G direct, the energy release rate is this one. Using this G90, energy release rate is this one, and the J integral using the discrete method, this one is this one, and this. Here you can see the energy release rate using direct and energy release rate discrete and continuum. They are quite equivalent to each other. However, the G90 degree blunt, this is it quite overestimate the other two. So hence we can say for this problem, the G direct method is more appropriate for determination of the energy release rate. So how will determine the J integral at the discrete domain? So we know the conventional line integral methods, and from there we have converted it into a volume integral methods. So from here we have tried to determine the crack path independence property. So here you can see when crack tip the following results can be concluded here. Here in these results, the path independence property has been maintained. However, when the atoms is taken near to the crack tip, the path independence cannot be maintained, and when this domain's size is very small, the path independence property cannot be maintained. So where these methods will be used? So here we have taken 4 different bicrystals. The previously was of 200 angstrom and 10 angstrom, 20 angstrom, 40 angstrom. The 3 will be taken here, and we will see what is the role of the distance between crack tip and grain boundary in the crack propagations. So here the stress strain plot. Here you can see A, B, C, D are the crack initiation points for different bicrystals. So here you can see for BC10, when crack tip is very close to the grain boundary, the crack initiation happens at the very early stage. For BC20 and 40, it's at a later stage, and for the D is is much later than other two. So we'll discuss only one case, the BC10 bicrystal here. Here you can see the crack tip is very close to the grain boundary. So we have determined the energy release rate using the previous method discussed, and the critical energy release rate for a single crystal. Here you can see the critical energy release rate is much higher than the energy release rate determined for the BC10 bicrystals. And when the crack will move here, the crack will make a kink here, and it will meet the grain boundary. And from there, the crack will further propagate into the crystal 2. So here you can see that here the crack tip will blunt because the stress intensity factor along this 0 direction, along 45 directions are very less than the stress intensity factor of the critical stress intensity factor. So how the crack initiation pattern varies for different bicrystals. Here you can see this is for BC10, and this is for BC20, and this is for BC40. So in BC10 there is a kink, in BC20 there is sharp crack will meet the grain boundary, and in BC40 this is similar to that of BC200 that we have discussed in previous in the earlier problem. Here you can see for BC10 the energy release rate is very high, very less, and for BC20 and 40 they are quite close to each other, and for single crystal it is more than all the three. Here you can see when we increase the distance between crack tip to the grain boundary, it will resembles to that of a single crystal, and when it is very close to the distance between crack tip and grain boundary is very close to, then at that time the crack initiation happens at a very low stage. So we'll discuss the role of the tilt angle in the crack propagation. Here you can see this is crystal 1, crystal 2. There is a tilt angle here theta. So when tilt angle is 1 degree, this is low angle grain boundary. So at this stage the crack will not deflect. It will move like a single crystal. When it is 20 degree, there is a deflection, and crack will in the crystal 2 the crack will deflect. And in 45 degree direction that has been explained in the previous problem 1. Here you can see the zigzag crack path, and in 60 degree there is a deflection of crack path. Similarly, there are other cases when the crack will also arrest. So in conclusion, here we have seen that the for crack bicrystal, we have shown the initiation, propagation, arrest, and reinitiation, and the zigzag crack path. The mechanics of the crack propagation has been justified using the near tip stress field, and further the role of DCG, the distance between crack tip to grain boundary, is studied, and using the CTOD method, using the CTOD method, and the overcoming of limitation of the near tip stress field has also been discussed. And later we have discussed the role of various tilt angle in the crack propagations. Thank you.